Is anything happening?
I don't think so.
I'm here. I just had to take care of something real quick.
Okay.
All right. How are y'all doing?
Doing good, sir. How are you?
Good, good. All right. We're going to remember today I've got to go get my COVID vaccine. So I'm supposed to be down at the Alamo Dome at like 2:40 or something. So I'm gonna end class at 2. That'll give me 40 minutes to get down there. So I already just set a timer, an alarm. So at 2 o'clock, we'll end class promptly. Okay, so I want to pick up with the notes from last time. If you have any questions on homework or anything like that, let's please hold off on those. Try and meet me for my office hours. If not, just email me or text me or call me if you're having specific issues. But let's just finish up the notes from last time. There was one problem in 1.1 that we didn't do. It was expressing the surface area of a sphere as a function of its volume. So the idea here is that if you look on our formula sheets, I've copied this, we have 2 formulas for spheres that are given to us. Now you may not have these memorized, but you should know that your formula sheet has them. Both of these formulas will give you the volume and surface area respectively. But in order to know what the volume or area is, you have to know what the radius is. Now, what we're being told here is to express the area as a function of volume. So somehow we want to know what the area is. And over on this side, we need to have something with volume in it, not radius, okay? So the way we're going to do this is we're going to write down, let's just write down the area formula. The area, surface area of the sphere is 4 pi r squared. And over to the side, I'm going to write the formula for the volume, which is 4/3 pi r cubed. Okay, so those are the 2 formulas we know coming in. I need to somehow get rid of this r and replace it with something that has volume in it. So I'm going to go to the other equation that has r and volume connected together, and I'm going to solve for r. So I'm going to try and get r by itself over here. So the first thing I'll do to do that is I'll multiply both sides by the reciprocal of 4/3, which is 3/4. If I multiply the left side by 3/4, I get 3/4 v. If I multiply the right side by 3/4, it'll kill off the 4/3, right? That's the whole idea here. And I'll still have pi r cubed. So I'm getting closer to having r by itself. I now need to divide both sides by pi. So why don't I write it this way? 3/4 pi times volume equals r cubed. So when I divide it by pi, I just put the pi down here with the 4. And then what would be my last step? Let's see, how about Laura? Is Laura around today?
I'm here.
Laura, what do you think our last step here would be to get just r, not r cubed?
You would take the cubic root of both sides?
That's right. So we're just going to take the cube root on both sides. And when we do that, we'll get r. And then this is what we have. It's ugly, but that's what we have. Okay, so now we have an expression for r in terms of v. And that's what we can go and replace this r with right here. So my new area formula will be 4 pi times r squared. Now r is going to be replaced with, oh, I forgot the cube root there, sorry. That was a cube right there. Cube root of 3/4 pi times v. And it's ugly, but that's it, okay? I mean, now if I want to know the area, somebody just needs to tell me the volume of the sphere and I can tell you what the area is. You don't need to tell me what the radius is, just tell me the volume, okay? So the idea behind this problem and the other 2 we did in class is, can you use formulas that you already know exist to somehow create new formulas that connect 2 variables together that aren't traditionally connected together? So that's what the last three examples were about. Any questions? Why didn't I do plus or minus over here? When Laura said to take the cube root on both sides, why not do plus or minus? So that way we always had to do plus or minus.
It can't be negative.
Mm-hmm. So it's only when you're doing even roots. If you're taking the square root of on both sides, you have to do plus or minus. If you're doing the fourth root, plus or minus. Sixth root, plus or minus. But if it's an odd root, then you do not need to do plus or minus. Okay, that's it for that. We are moving on. So we are going to go to 1.2, which, okay, so this section, catalog of essential functions, all this section is about is you're coming into Cal 1 and you should have like a toolbox full of things that you already know, okay? And this section is just about reviewing all the different types of functions that you should be familiar with and kind of what they look like and the way they behave. And kind of, we're just going to wrap it all up into one section and quickly review them, all right? So the first type of function that you should know are the power functions. We should all know that x squared, can you all see this okay? Should I make this a little bit bigger? Is that a little better?
It looks fine.
It's fine. I don't want to go too big here. I'll do that. Okay. So power functions. This is x squared. That's what we're looking at here. That's just your standard parabola, right? So both ends of x squared go up, right? So x cubed looks like that. Left side goes down, right side goes up. Okay, x to the fourth power, both sides go up again. So it's very much like x squared. Now they are different. Here's x squared in red, and then the green one is x to the fourth. So the idea is that if it's an even power, x squared, x4, x6, both sides go up. But if it's an odd power, left side goes down, right side goes up. So I'm showing you here odd powers there. That's x cubed and x to the fifth. They're similar. What we want to understand is the basic behavior, all right? All right, so let me ask a question here from last class. Claire, is Claire here?
Yes, I'm here.
Claire, looking at this function, this is x to the fifth power. Is this function always increasing or always decreasing?
It would always be increasing.
Increasing. So the idea, everyone, is, and I really thought about this because today is pretty important. Imagine that you're a person walking on this graph, right? And you were always going to walk from left to right because we read graphs from left to right. So if you're walking on this graph, does everyone see that as you walk to the right, you're always going up, right? You're always increasing. Now, if we were to do x squared, that wouldn't be the case, right? There would be, you know, on this side over here, we'd be going down, and then when we reach the bottom, then we'd start going up, right? So we're going to be decreasing over here until we get to 0, and then once we get to 0, we start going up, right? All right, so those are our power functions. Now, the negative power functions. So notice this is x to the -1, x to the -2, x to the -3. And remember that whenever you have something to a negative power, so like when you have x to the -1, you can rewrite that as 1 over x, right? If you have x to the -2, that's the same as 1 over x squared. That's just a property of exponents that if you have a negative power, you can drop it down, right? So here are what these negative power functions look like. The one we're looking at right now is 1 over x. It has a vertical asymptote at 0, and that's because you cannot plug 0 into this function. Here's 1 over x squared. I like to think of this as, I refer to this as the volcano function because it's kind of like a volcano, but it goes up in the middle like forever, okay? And let's see, x cubed, or 1 over x cubed looks a lot like 1 over x, doesn't it? Okay. Here's 1 over x squared, the volcano. Here's 1 over x to the fourth. Again, very much like 1 over x squared. And then 1 over x to the 5th is very much like the others, 1 over x and 1 over x cubed. So just understand the similarities and differences between these negative powers and how they differ significantly from the positive powers, right? Here we don't have any asymptotes, no vertical asymptotes at all. All right, root functions. The square root of x, the cube root of x, the 4th root of x, the 5th root of x, the 6th root of x. So the standard square root function looks like this. And we should all be comfortable with the idea that with the square root of x, there should never be any picture over here, right? To the left of 0, there should not be anything because you can't plug negatives in. So a square root function almost looks like a parabola that's been cut in half and then like laid over on its side. That's what the square root function looks like. Now the cube root function, can you plug negatives into the cube root? Can you plug a negative into a cube root? Can you take the cube root of 8? Yes, you can. I'm sorry, the cube root of -8 is what I meant to say. So we can have cube roots of negatives. So when we graph it, see, we do have picture over here for negatives. See, square root can't plug negatives in. It will only exist to the right of 0, but the cube root will exist everywhere. How about 4th root? Can you take the 4th root of a negative number?
No.
No. So it should look a lot like the square root function. 5th root should look a lot like the cube root. Should exist everywhere. And then the 6th root, we should not have anything in negatives. So here's your square root, 4th root, and 6th root all together. So they have little variations. They are different, but they all have the same basic characteristic. Starts at 0, goes to the right. And these graphs, they do grow. They keep going and going. They keep getting larger and larger. I mean, like this graph will keep going up and up and up and up. It's slow, but it does go up, okay? It's a very slow growth, but it does keep going. Any questions?
Where did you go so you can open up these or mess around with these graphs? Is it somewhere in
like if you want to be able to do what I'm doing in my notes?
Yeah.
Okay, let me see if I have them. I may or may not have them available to you. I know for my Cal 3 class I do, but I don't remember if I made them available to you. If they are here, they're going to be in the Canvas page under notes. So let me see, files, course notes. No, they're not here. Okay, so you know what I'll do? I'll put them in here, okay? But the thing is, if I put them in here, they're not PDF files. These are files, they're called computable document format, which means you have to download a player from Wolfram's website. So I'll send that in an email, okay? For those of you who are interested in being able to open up my notes and do the same thing I'm doing. I did all these notes. I'm not a computer science person, but I taught myself the language here. So for those of you who are computer science, this is all the code that I had to write up to make this happen. So if you're computer science and you like this sort of thing, you'll be able to open up my code, but you won't be able to edit it. So, okay, keep going. Yes?
Yeah.
Root functions. All right, polynomial functions. Polynomial functions are roller coasters, basically. All right. So let's see if these look. Let's go with a degree 1 polynomial would be a line. A degree 2 polynomial would be a quadratic, but we can kind of change where it is. A degree 3 polynomial, do these look familiar from college algebra, right? Polynomials. Now, with polynomials, the whole idea behind a polynomial is that you've got these nice smooth curves, except lines. Lines are straight, but other than that, they're nice and smooth and curved. They're either going to go down on the left and up on the right, or they can go, up and up, or they can go up and down. this end behavior that we learn in college algebra, like how to look at a polynomial and determine its end behavior. All I need you to know here is that polynomials look like smooth, curved, continuous functions, meaning you can draw them without picking up your pencil. All polynomials you can draw without picking up your pencil. All right. Now in college algebra, what you may have, well, I know you did, is that you studied how to draw these, right? Didn't you do some graphing of these in college algebra?
Yeah.
Sketching polynomials?
I think there's some way to figure out whether it's going to turn or bounce back up.
Yeah.
It's been a while. So.
Exactly, but you did do something. What you did not do, okay, I can guarantee you what you did not do is when you were drawing these, you may have figured out like whether or not like at this point you kind of bounced off, or if you crossed through. That was called the multiplicity of the root and all that stuff. And here you could find the x-intercept. What you did not ever do is actually try and figure out that point, the actual low point there. And hopefully your college algebra teacher told you that finding the highest and lowest points on a polynomial is something you do in calculus. That's going to be a major, major goal of this course, is if I give you a function, can you find me the little peaks and valleys? Okay, that's going to be a major goal. And it's going to require a lot of calculus to build up to getting to that goal. And the reason is that, the reason why it's important to us is because if you take an arbitrary function, let's say that this is time, and let's say this is profit. Okay, I'm just going to take like a economics. So you own a company, right? And you're like, okay, you know, this was January, and then maybe this is February, and you know, this is like every month you take a look at your profit for the months, and you can see like profit was up, and then, you know, down, and then up, whatever, right? It would be important for you to be able to find these high and low points. Okay, you say, what happened here, right? Like a profit was, this is the highest profit. Like what was going on here, right? What was going on? That's when we hired, you know, so-and-so, you know, look what happened. We hired them, and then look, our profits started dropping, right? And then, this is when we fired them. Oh, we fired them, and our profits started going back up, right? Whatever, I'm just saying, finding highest and lowest points of graphs is going to be a major goal for us, because it's not easy to do in general, not at all. There's only one function right now that you could actually tell me the highest and lowest point of. There's only one out there that you could do, and that's a parabola. If somebody gave you a parabola right now, and when I write this down, this may look familiar. We all know that parabolas either look like this or like that. And so this point right here had a very special name. What was it called? The lowest point here or the highest? The vertex?
Yeah.
And you were actually given a formula in college algebra how to find that. It was called the Vertex Formula. And you were told that we call that point HK. And the formula for H is negative B over 2A. And K is just F evaluated at H. But it's not important that you like remember all this right this second. What I'm trying to tell you is that in all of the math that you've done, there's really only one function that you can find the lowest and highest point of, and that's the parabola. Our goal is for me to be able to hand you any function and you find the highest and lowest points. All right? Okay, getting back to notes. And when we get to this point, when we're doing it, I'll actually show you where this formula comes from, because this formula actually comes from calculus. We're going to prove that this is true. All right, polynomials, blah, blah, blah. Okay, rational functions. You probably remember these sucked, okay? You have vertical asymptotes, horizontal asymptotes, x-intercepts, slant asymptotes. These are weird looking end behavior. Do y'all remember this? These are just nasty, okay? And we can't like just summarize them quickly. every rational function is different. They can look so different from one another. You know, so just changing one little thing changes the whole picture. So rational functions, a lot of them have vertical asymptotes, they have horizontal asymptotes. Those are characteristics that we want to be familiar with. So when we're looking at a rational function in this class later, we need to kind of understand, oh yeah, this may have some weird, crazy things going on. All right, that wraps up college algebra. Then you took pre-cal, right? And you learned about the trig functions. And there are 6 basic trig functions, right? The sine function, here's the sine function. You learn that the period of sine function is 2 pi. The amplitude is 1, right? Cosine, right here in green, looks very much like sine, but it's kind of shifted. Then you learned about the tangent function, which has these vertical asymptotes. And then you learn about the other 3, which are just the reciprocals of these functions: cosecant, secant, cotangent. Does that look like a mess to you already, right? So my expectation is that you have some framework within your mind about what these functions look like, right? You need that moving ahead. And if you've forgotten at any point, your formula sheet does have a lot of these. So if you scroll down to, here are the graphs of the basic 6 trig functions right here, right? So if you've forgotten what cosine or tangent looks like, you know, here they are. Oh, and I should also point out that these trig functions are periodic, and that means they keep repeating. So if I were to show more of the sine function, it just goes like in both directions forever, right? It's not just like one period. All right. Oh, this is college algebra. I don't know why I put this after trig. This is college algebra also. You learned about the exponential functions. Exponential functions are functions that look like this: a to the x, where a is a positive number and a is not 1. So e to the x, 2 to the x, 1/2 to the x, those are all exponential functions, and they all look like this. They either increase as you move from left to right, right? This is an increasing function, or they could also decrease. And so you can have exponential growth, which would be the red one, or you can have exponential decay, which is the green one. So let's see. Yeah, I think that's all I say about that. Now, the log functions are the inverses of the exponential function. So what we're looking at right now, this red one is e to the x, just so everyone's clear. We are now looking at e to the x. The inverse of that function, the inverse of e to the x, everyone should know, is natural log of x. And so if I graph that, here it is. And if I show the identity, that means if I draw a diagonal line, perfect diagonal line, right through the origin, these 2 graphs should be reflections of one another over that diagonal. So if you like kind of turn your head, you can see that they're like mirror images of one another. Do y'all see that over the diagonal? All inverse functions behave that way. So if you have a function and it has an inverse and you graph both of them, they will always be a reflection over the identity. I'll show you another one. Here's 2 to the x. Here's its inverse. And let me take the others out of here. So there's 2 to the x and there's log base 2. So reflection. And then I'll do 1/2 to the x. That's exponential decay. And if I graph log base 1/2, there's its inverse. You know what? This scale is not perfect here. It doesn't look like it's a reflection. That's because my scaling is off on my picture. All right, I want to say something else about the log functions because I know this is going to get some of you in trouble later. So you know what? Let's do it this way. Everybody paying attention? This is important. All right. Braxton, you here? Braxton?
Yes, sir.
I see Braxton. There
Yes,
you are.
I'm here. Sorry, I had to unmute myself.
No, it's all right. So Braxton, I have a question about this exponential function e to the x. If I were to ask you to start plugging in values of x here and keep plugging in values of x that are bigger and bigger and bigger, where's the function headed?
To infinity.
To infinity. Okay, perfect. That's the answer I wanted. Everyone needs to understand that there's like this arrow here. And so as you move to the right, the graph goes to infinity. Now, Braxton, same question, the other direction. So now if I start plugging in values that are negative and I keep going in the negative direction, is the function approaching something? Can you tell? I'll graph a little more of it for you.
Is it approaching 0?
It is approaching
or
0.
Negative infinity.
So when Braxton
Okay.
says that it's approaching 0, what he means is that as the x value goes to negative infinity, so as Braxton is saying, as I plug in values of x that are getting more and more negative, e to the x is headed to 0. Does everyone understand that? As x goes to negative infinity, as we start looking out to the left, the value of the function is getting smaller and smaller and smaller, getting closer to 0. On the other hand, as x goes to positive infinity, that means out the right-hand side, e to the x is headed to positive infinity also. So as you move out to the right, the graph grows and grows and grows. Everyone clear on that? Yes?
Yes.
Okay. So I'm going to ask somebody else the same questions, but for the inverse of this function.
Sir, may you please explain that second part?
Oh, I can't undo that. Okay. The second part, this one, you mean x goes to infinity means
yes,
e to the x goes to infinity. Okay. So if you start plugging in values here, okay, 1 or 2 or 3, your y values are up here, right? So the bigger that x gets, the bigger x values you plug in, the bigger the y values are going to be, right? So as x gets really big, the function's value gets really big. Does that help clarify that?
Yes, sir. Thank you.
Okay. And then the other direction, as x gets really big negative, right? As x gets really big negative, the function gets small. It goes to 0. And that's because you have a horizontal asymptote. We should clarify something here. When I say a big number, I mean, I have to be clear. If I say a big number, I have to tell you a big number positive or big number negative. Because, you know, the number 1 million, let's say, is a big number, right? Negative 1 million is not a small number, it's a big negative number, all right? A small number would be a number really close to 0, 0.000001 or something. That's a small number. So small means really close to 0. Big means, well, either big positive or big negative, all right? So just so we're all on the same page with our language. All right, so here we go. Dilpreet is up, and I want to ask for this graph. I'd like for you to tell me, as x gets really big, what does this natural log function do? Where does it go? So if x is getting big, where's the function headed?
Towards the negative, so number goes smaller.
So if I plug in 2, let's say, the value is here, right? Whatever value that is. If I plug in 3, the value is here, right? Which has now gotten bigger, yes?
Yes, sir.
If I plug in 1 million, then that's going to be further
Bigger.
up, isn't it? So as x gets bigger, what's happening to the y values of the function? Are they getting bigger, smaller? What's going on?
Bigger.
Bigger, right? Look at this arrow, right? Implies that this grows and grows. It's not very fast, but it is getting bigger, right? So we would say it goes to infinity. So for the natural log function, as x gets big, so does the function. All right, how about Natalie? Natalie?
Yes.
So Natalie, you get the other side. So if, and this is a trick question, I'm sorry, Natalie. Where's Natalie? Oh, there you are. Sorry, Natalie. If x goes to negative infinity, so if I'm starting to go out this direction, what does the natural log function do? And again, I apologize, this is a trick question.
Well, the numbers will get smaller as it approaches the y-axis.
Okay, so we can't go this way, everyone. Do y'all see that? There is no graph of natural log over here. You cannot plug negatives into log functions, right? So that's why I'm saying this is a trick question, because I'm asking Natalie, what happens, Natalie, if I plug these really big negative numbers into natural log? But you can't, right? You can't. What I do think Natalie noticed is that if I start moving my x values closer to 0, right? Imagine I'm getting closer to 0. Where is this function headed? Where's that going?
Down.
Down to negative infinity, right? Down to negative infinity. So the way I'd write this is this. As x starts going to 0, natural log of x heads towards negative infinity. That's the way I'd write that. As x gets closer to 0, the natural log function starts to dive down, right? As x gets bigger, going to the right, the natural log function also gets bigger. But I can't go to negative infinity because it's not in the domain. Any questions? Do I need to clarify any of that? Okay.
So is it like every single time whenever x gets 0, so every single time it's just gonna be a infinity?
Negative infinity for the natural log function. And actually it's for all these log functions, well, not that one. All these log functions do the same thing. As you go towards 0, they start to dive down to negative infinity.
Got it, that makes sense, thank you.
Mm-hmm. Okay, now, that's it. That's the toolbox of functions you should be familiar with. Those are all the functions I expect that you've had some experience with coming into this class. Everything we do now, we're just going to build off of this. But you also need to understand that with every function, we have transformations. So we all know that if you take the function, like we all know what this looks like. Well, I hope we all know what this looks like. X squared, right? It's just zero parabola. But we can transform it. We can have a different function where we do x squared and say like +3. And what that does is just takes that x squared function and moves it up, right? Or we could do something like this. Another function where we do, instead of x squared +3, x +3 squared. That does not move it up. Can someone tell me what this does? It does move it, but it doesn't move it up 3. What does it do?
You can FOIL it out, make a polynomial.
You could FOIL it, but just by looking at it this way, does anyone know what the transformation is? Which way it moves?
Does it shift left 9 times?
It moves left 3 spaces. So when you add a number on the outside of the function, it moves it up or down. But if you add the number inside the function, then it's going to move it left or right, and it's opposite of what you think for left or right. Because +3 would make you think go to the right 3, but it's actually left 3. Now on the outside, when you add the 3 out here, it does do what you think. Up +3 is up 3, down 3 is -3. So that's what I said here. F of x, if you know what a function looks like, adding a number moves it up by that much, subtracting moves it down. If you add the number inside the function, it shifts it to the left. If you subtract the number inside the function, it shifts it to the right. I'll give you one last one.
Aren't the square root functions a little different though too?
Oh, they all do the same.
Okay.
Yep. This is for any function. You'll get this shifting.
Okay.
So let me give you this one. x minus 4 squared minus 3. So what that's going to be if we graph it, it starts out by being just our general x squared function. Now, what does the minus 4 do?
To the right.
Right 4. 1, 2, 3, 4. Here's 4. So now it's here. Okay, and what does minus 3 do?
Shifts it
Down
down.
3.
Down 3. So 1, 2, 3. Here it is. Now here's our final picture. There it is. Okay. So all of these functions that we've kind of studied or know, if we do anything like this, we can transform them, move them up, down, left, right. And then we can also stretch them or flip them over by multiplying them by a number. So that would, the example of this would be, let's say we take, let's go with x squared again, because it's the easiest one to work with. If I instead ask you to do 4x squared, since 4 is a number bigger than 1, it's going to stretch it vertically. So instead of looking like this, that's x squared, it's going to stretch it. So it's going to now look like more like this, just like pull it vertically. If this number here in front is a fraction, like 1/2, it's going to actually flatten it out or stretch it horizontally. And then what if the number in front is negative? Like negative x squared or negative 4.
Flip it.
Flip it over
the x-axis. Okay, so that's what all this says. And again, this is all college algebra, pre-cal stuff. We're still kind of in a review here. So I'm not saying that you need to go back and like review every single thing from college algebra here. But as we move through this course, I'm going to bring some of these things up. And if you're like, what? You know, you might want to just put like little asterisks next to that and make sure you get clarification on it. All right, so yeah, I won't do transformations. Okay, combining functions. So when we're given two functions, right? Two different functions, we can always combine them together. And we have what we call the 4 arithmetic operations. We can always add two functions together. We can always subtract two functions. We can always multiply two functions, and we can always divide two functions. And that's because we've got 4 operations when it comes to arithmetic. But there is a 5th operation between two functions that is not an operation we have on numbers. So what I'm getting at is when you're learning about numbers in grade school, they tell you, okay, you can do like 4 plus 3, 4 minus 3, 4 times 3, 4 divided by 3. But they never tell you to do 4 composed with 3, right? Like that makes no sense. We don't know what that means. But with functions, you have this thing called composition. In composition, I know when I learned it in college algebra, I wasn't quite sure why we needed to do composition. In this class, you will see why composition is important to understand, all right? So I want to take some time to make sure that you can do composition. I'm not going to do examples of addition, subtraction, multiplication, division, because I would expect you could do that. But I do want to do composition. So let's do this example. And I think I'm going to copy this. Oops, wrong button. I need to figure out why that always comes in so big like that. All right. So for these two functions, we could add them together. Okay, I'll add them, all right? All right. If I add them, that's the notation to add them. So all that means is you just take the two functions and add them together. And you get a new function, right? You get x squared plus x. I didn't need the parentheses. Let's see, the x squareds cancel. You just get 1 plus x. Okay, so that's what you would get if you added them. If you subtracted, you would just put a minus sign here, right? If you multiplied, you would just do a dot here and you would do FOIL. And then division would create just a fraction. But what I'm really focusing on is this, f of g of x. That's what I want to make sure everyone understands. Now, you may have, in college algebra, learned that as being fog and goff. Yeah, no? I don't teach it that way, but I know some people do. Okay, so what does this mean? This means we're going to take the f function, and inside of it, we're going to put the g function. I like to think of it this way. When you do f of g of x, what's happening here is that x first gets sent through this machine, this function. It gets sent through g first, and it comes out as a number. And then that goes through the f function and comes out as f of g of x, which is your composition. So remember we talked about functions, take a number in, spit a number out, right? Input, output. Composition is where you have two functions. And so it's like a chain. The input goes through one of the functions first, and then that answer goes through the other function and comes out as a final number. Okay? So let's do this here. When we write f of g of x, we are going to now write f, and then inside here we replace g of x with what it is. And in this problem, it's x minus x squared. And now, let's see, Natalie, I called on. Carla, is Carla here?
Yes.
So Carla, when I write down f with this stuff in parentheses, what am I supposed to do with this?
You plug those in instead of the x in the f of x function.
That's right. So I'm just going to take that x minus x squared, and I'm going to go into this f function here, and I'm going to replace that x with that. So that becomes, so no more f here. It just becomes that thing, x minus x squared, but then squared plus 1. Does everyone see that? This thing in green gets plugged in for that x into the f function. And so we have to plug it in here and then square it and then add 1. And that is the composition. That's f of g of x. Now we could FOIL this out, but I'm not going to. Now, how about this? I didn't ask for it, but could we do it the other way around? Could we do g of f of x? Well, that would be different. It would be g is going to get f of x. Instead of f getting g plugged in, we're going to go g gets f plugged in. So g, let's see, what is f of x? It's up here, right? X squared plus 1. And now that piece gets plugged into the g function for x, which up here is this. I'm going to have to zoom out a little bit so I can get this all on the screen. So I'm going to take the g, and I'm going to replace this x with x squared plus 1. So I'm going to have x squared plus 1. And then minus that thing in blue again, x squared plus 1 squared. Any questions on that? I took this is f, and replaced this x with f here and here. Now, I bet you most of you did f of g of x in college algebra and g of f of x. But what about this? Why not do f of x? I mean, there's nothing that tells us we can't. So this means we're going to take f, and inside we're going to plug in f. So we start out with f, which is x squared plus 1, right? And then we're going to plug that back into f. So that means we've got to take that result, we've got to take this here in yellow and plug it back into x squared plus 1. So it should be x squared plus 1 squared plus 1. That's weird. That's weird. That's that yellow piece going in right here, which means right there. And so we have to take it and square it and then add 1 again. Now I'm going to stop here, but I mean, there's nothing stopping us from doing multiple compositions. Like this would mean F, and inside of F goes G, and inside of G goes F. I did too many of those. 1, 2, 3. So first F gets plugged into G, then that answer gets plugged into F, and then that answer gets plugged into F again. So there's no limitation on how many compositions you can ever have. The ones in college algebra are usually just these two. Are just these two. Okay, those two are the ones you usually see. Are there any questions? All right, so in Calculus 1, we are not as interested in doing compositions the way we did in college algebra as we are about doing decompositions, which is something you don't talk a lot about in college algebra. So what we're going to do here, this should be new to a lot of you, is I'm going to give you a very complicated looking function. And we are going to get a lot of practice with this later. I'll give you a very complicated looking function here. Here it is in yellow. And I'm calling it capital M of X. And what I'd like for you to do is to see if you can't break that M down to be the composition of 3 functions. To realize that this M could be rewritten as some function plugged into another function plugged into another function. Okay? So this is the way I like to do this. Imagine that you had to actually plug a value of X in here, right? Imagine that you were going to take a number and plug it in. The first thing that would happen if you plugged a number in would be everything in this parenthesis, right? You do the x squared plus 1 first. So that would be the first thing that happens. What would happen next? What does this 5 mean?
Power of 5?
It means raise it to the 5th power, right? So, I mean, technically this really means you take sine of x squared plus 1 and you raise all of that to the 5th power. Okay, so if we were to plug in a value for X, we would do everything there in green first. We'd get a number, right? Then we would take sine of that number. Then we would raise it to the 5th power. So do you see that there's 3 things happening there? The green, the blue, the yellow, in that order. So when we come up with our composition of functions, we just have to come up with 3 functions that would generate that same thing, f, g, and h. Now, you can look at this one of 2 ways. You can start working from the outside in, or you can go from the inside out. I'm going from the outside in, and that's because of what we're going to do later. So the last thing that happens is that we're going to raise this to the 5th power. So I'm going to put x to the 5th here. The thing that would happen, I should say before that, would have been the sine function. So I'm going to put sine x. And then the thing that happens before that would be the green, which would be the x squared plus 1. Now, if you can check this. If you take this and plug it in for x, you would then have sine of x squared plus 1. And if you take that and plug that into this x, you would have the original function. So we've broken it down. We've broken a complicated function down into the composition of 3 functions. Is that clear or no?
Yes, sir, it's clear.
Okay, so here's why we do this. Because this function by itself, if I asked you right now, take a look at that function. Everyone in here is going to have a really hard time understanding what that function looks like and everything else, because it's just a combination of all these different things, right? So in calculus, what we do is we try and break functions down into their like elementary pieces. Everyone here knows what that function is, right? That's just a parabola moved up 1, right? Everyone knows what the sine function is. It's one of the functions you should know, right? And then everyone knows that that's a power function. So it's kind of what we do is we kind of break it up and conquer each piece individually, as opposed to trying to look at the whole thing. Okay, we'll get more practice with this. I have 10 minutes. I think I'm ready to move on to the next section. All right, so this is officially where Cal 1 begins, right here, all right? The limit of a function. So if you were to look at calculus, all right, and you're all aware that there's like Cal 1, Cal 2, Cal 3, and all of those courses, everything, if you were to draw like a chart here, the limit is the heart of all branches of calculus. Calculus cannot be done without the idea of the limit, right? So everything we do in Cal 1 is based on the limit. Everything we do in Cal 2 is based on the limit. Cal 3, everything's the limit. Differential equations, everything's got to be based on the limit. Engineering analysis, everything is based on the idea of the limit. And it's a simple idea, but it's hard to execute the limit, all right? Visually, it's, I think, within grasp of most people to understand what a limit is. So we're going to start with the visualization of a limit, okay? Before I actually get to a hardcore example, I'm going to give you a function real quick. I want to use the same one here. Negative x cubed plus 4x squared. All right, so I'm going to give you a function here. I could ask you to plug values into this, couldn't I? Like I could ask you to plug in, let's see, I'll do it down here. What's f of 0? So what happens if we put 0 into that?
0.
Everything goes away, you just get 0, right? So do you agree that this point would be on the graph in blue? 0,
Yes.
Plug in 0, you get 0. Let's try 1. What would f of 1 be? Okay, so you cube 1 first and then make it negative. So that's -1, and then you square 1 and multiply times 4. So you're going to add 4. So this should give us a 3, shouldn't it?
Yes.
Okay, so we plug in 1, we get 3. What we are doing right now is algebra, right? This is algebra. Somebody gives you a function, tells you to plug a value in, and you should be able to spit out the answer. Yes? You can tell me what's happening exactly at every point. You want to know what happens at 2? Just plug 2 in. You want to know what happens at 3? Just plug 3 in, right? Calculus is not about this. It's not. It's something different, right? So here's the visualization. All right. I want everyone to look at the function we were just looking at. Okay, this is it. I've already graphed it for us. Now, I know you can't really see it because it's gray, but do you see that at 2, okay, do you see that at 2 here, if we were to plug 2 into the function, we could do that, right? It's going to spit out the answer 8. Do you trust that that's right? At 2, the value of the function is this red dot, that's 8. Yes? That's algebra. What we're interested in now is calculus, which means you're not allowed to look at 2 anymore, okay? Let's not look at 2. I'm going to hide it from you. No, I'm not. There. So now you don't know anything about 2, okay? Just forget anything you've ever known about what's happening at 2. The question is, what is the function doing as we approach 2? So the way you think about that is if you were a person walking on this graph, okay? So look, I don't have it written down here. What is the function doing as x gets close to 2. Okay, so that's why I'm going to write that, x with an arrow to 2. What's happening as x gets close to 2? So if I'm standing on this graph right now, is this person close to the x value 2 right now? So 2 is here, right? Am I close to 2 right now? I'm at like 0.5 or 0.6. Am I close to 2? I could get closer, couldn't I? Yeah. So if I start walking along this graph, now my x values are getting closer to 2. What is the function doing? What are the y values doing? What are they getting closer to? What do they look like they're getting closer to?
They're increasing, so they're getting closer to 10.
Okay, 10 would be up. Well, I don't know. This graph doesn't seem to get up to 10, does it?
9.5.
I guess approaching 10.
10 is up here, though. I'm saying if I keep on getting closer, see my x values are getting closer to 2 here? My y values, how high I am? Aren't they all kind of going up and up and up? Aren't they gonna kind of max out at 8?
Yes.
Y'all see that they're gonna kind of max out at 8?
Yes.
You sure y'all see that? I'm gonna clear this out of here. I have another way of showing it to you. If you start moving along the graph, okay, the blue is the x value. The purple is the y value. As the x value, the blue, gets closer to 2. See it getting closer to 2? What is the purple y value getting closer to?
To 8.
What does it look like? Looks like it's getting closer to 8, right? Let me get even closer. We're at 1.99 right now, and look at our y value, 7.95, getting closer, right? Let's get even closer. I'm at 1.99, and I'm really close to 8, right? Really close to 8. Now, would it change if I came in from the other side? So let's say I were to come in from here and start walking towards 2 from the right to left. If I start walking closer to 2, what is my y value doing over there?
Getting lower.
Still approaching 8.
It's still approaching 8 though, right? So let's see. As I start coming in here, look at the right-hand side. The black number is the x value. It's getting closer to 2. And the black number up here is the y value. Look what's happening. I go above 8, right? But as I get close to 2, right? As I get close to 2, let me take the other one out of here. As I get close to 2, the y value is approaching 8. It's a little bigger than 8, but do you see it's getting closer and closer to 8? Okay, so this is our first real introduction to this idea of a limit. We don't care what's happening at 2. Let me say it again. We do not care what is happening at 2. We care what's happening near 2. Near. And this creates something that's very subjective. I'm almost out of time, so I can't do much more with this. So I want to just talk about this quick point. This word near is troubling, okay? Because let's see, Cody, am I near you right now?
Not really, no.
Not really. Compared to the sun, are we near each other?
Yes.
Right? We are, right? So I'm really, really far away from the sun, but I'm pretty near to the sun compared to Alpha Centauri or some other star, right? So near is subjective. It is subjective. And we're going to wave our hands at that in this class, all right? Mathematicians have to deal with that later, and we have precise ways of dealing with it. But in this class, when I say near, it's going to be what you would think is near. Like, do you think that 2.088 is near 2? Do you think that's near 2? Yeah, we're just going to say it is, all right? We're not going to say, well, it's relative. We're just going to accept it. Okay, I want to show you one more. I'm almost out of time, but I think it's important for me to show you one more. Okay, so here's a function. This is a piecewise function. If you were just being asked on this function to figure out what's happening at 2, can everyone see that at 2, I have a solid dot up here? My answer is 8. Y'all see that? Yes?
Yes.
Okay. All right, now this is calculus. So I don't care about what's happening at 2. So I'm going to hide that from you and show you the rest of the function. That's what the function looks like on the sides. So if I start to ask you what happens as we get near 2, do y'all see that if we start coming in from the left side, are my y values approaching 8?
Yes.
Yeah, they are, right? They are. But if I come in from the right side, are my y values approaching 8?
No.
Approaching 4.
They're approaching, looks like 4. So we're getting different things from different sides, aren't we? Right? And so this is going to lead us into the rest of, next week we'll meet, right? For homework, just try and do everything you can out of 1-1, and I'm looking to see what the homework, if there's a homework assignment out of 1-2. Yeah, there's a lot. Now look, don't get too frustrated with 1-2, all right? Because really, like I said, today calculus begins. The limit is I've taught classes in the past where I don't even do 1.1 and 1.2. I don't even do them. I just start in 1.3. But I wanted to at least have some time to review some stuff. So do what you can out of 1.2. Don't stress out about it. Just do what you can, all right? And then we'll come back next week and we will get into 1.3. And I think you'll enjoy it. We'll see.
Hey, Professor.
Good. Any questions?
Yes.
Again, sorry I have to end class for the COVID thing, but.
Should I just message you later so you can go?
What's that?
Should I just message you with my questions so that way you can go?
Okay. All right. I will look at it in a second. Okay, everyone. Have a good day. Have a good weekend.
Hey, Professor.
Yes.
I did email that lady you told me about.
Yes.
But I haven't heard anything back from her.
Really?
Mm-hmm.
Wow. You emailed her on Tuesday?
Yes, sir. I emailed her on Tuesday, right
Wow.
after you said it. And also,
I'll call her.
okay. And also I did email my advisor too today.
Okay. Okay. I'll get in touch with her.
All right. Thank you.
Okay.
Thank you, Professor.
Yes.
I was just saying thank you.
Oh, okay. Have a good one.
Have a good evening.
Have a good weekend.
Bye.
All right.